is it? It's 2010, 04. I thought it was 2012. That's how I put it. If I write the date that way, that's the easiest way for me to sort files by date, like the videos and other things. So also, I gave a bit of information that was not correct. Going to YouTube and putting in my name doesn't get you any of these videos.
Yeah.
But putting in my YouTube name, all is one word,
Oh yeah, that gets
lets you search all of them. So you got to put in Paul G. Beliveau, all one word. And if you put that into YouTube, you'll get all my videos. And then you can search them by date, which I always put in this way. Or you can search them by class.
Did you give your middle name?
You have no class.
I've been told that before.
I just searched that video in the Monkey's Got Chips one, and then it brings me out to...
How to gets you the rest of my channel?
Yeah.
That's a great way. Costa Rica. Oh, yes, also if you Google Costa Rica Monkey Got Chips,
It's got chips now?
You will get to my YouTube channel. Now, exponential decay. Okay, negative exponents. If you remember those, this is a little bit easier.
Oh no. Shoot
For
me down.
exponential growth, we talked. The big example I gave was about the chessboard, okay, the grains of rice, and the ancient wacky Persian fellow.
ASON.
Now, for exponential decay, this is a slightly different story, but it can be a similar principle. I don't have as good a historical example, but I've got one from physics, Half-Life. You guys ever heard of Half-Life?
Unfortunately.
Not the video game Half-Life.
They're making
Counter-Strike.
Portal 2.
Fantastic. Okay. The way Half-Life works is when you have a radioactive substance, it is unstable. And its very atoms do not have a good balance of protons, neutrons, and electrons, and it is trying to achieve balance. So it is shedding particles, subatomic particles, which will kill you if you walk too close to these substances.
Mr. Miyama.
The way it
You have a friend.
The way it sheds these particles, okay, is it sheds them. It sheds half of its total particles in a certain amount of time, and that's called a half-life. And what the particles are actually doing, what they're actually doing, is each atom is turning into lead.
Don't all chemicals have a half-life? At some point? Like,
Oh,
like
God,
after a long enough time?
These aren't chemicals; these are actual elements.
And these are...
And I'm not sure if
radioactive elements?
these are radioactive elements, yeah, in particular. And I don't think they all have exponential decay. I don't think half-life is the right term for all chemical.
Even though they may like deteriorate after a while.
Yeah, a lot of them do follow this pattern. So we're going to get into that. We're going to do a tiny bit of toxicology next week.
Oh, great.
Tiny bit. We're going to poison somebody, hypothetically.
Sweet!
Okay, the idea with half-life is if I start out with 100 pounds of, I'm going to make up an element of selenium.
Why not
Okay.
Serenium?
I could have been, okay. 100 pounds of selenium. And selenium has a half-life of...
Is there such a thing as selenium?
I have no idea. There probably will be after this video get out. Okay, so guys, this element has a half-life of 10 years. That means it is turning into lead at a very particular rate. It means that when time equals 0, let me do a little chart.
Oh, God. How about not?
Time, weight. At 0 years, we have 100 pounds of selenium. But he's wasting away, our element named Phil. 10 years later, we have 50 pounds. 20 years later, we have 25 pounds. 30 years later, we have 12.5 pounds.
Oh, so it just keeps halving?
Yeah. 40 years later, we have 6.25 pounds.
But then, doesn't that theoretically mean it never gets to 0?
This is, hold that thought for 1 sec, 3.125 pounds, etc. Sarah just raised a great point. Theoretically, and yes, mathematically, this gets back to that idea of asymptote that we talked about. Mathematically, this never reaches 0. However, we use it to model, if there was a real element called selenium with this half-life, it does have a finite number of atoms. And there will be a magical moment when that last atom transmutes from selenium into lead by shedding its unstable particles.
No.
Okay, but, so, this is not 100% accurate. The math I'm about to teach you is not 100% accurate for predicting how this element will behave.
It's 99.9.
99.99999%. I mean, seriously, who's going to count atoms? I mean, really. You have a lot of free time. Yes, Amanda?
Why?
You count everything
You're
else, why
going
shouldn't
up
you?
in time of like tens, and then you're going down by half.
Yeah, excellent. Amanda, I'm glad that actually makes your head hurt a little bit. Because no, that means you're thinking. If you're going up by the same amount every time, this is what's called a linear progression. And we spent the first part of this year studying lines and how you can use lines to model stuff. So as time goes up linearly, the weight goes down by halves. As you add 10 to the years, you've got addition going on over here, you've got division going on over here. That's why these patterns don't work like the nice simple proportions you learned in middle school, and this is why we can't use lines to model them. Because when you've got addition going on over here and multiplication going on over here, it's going to be wacky. How wacky, you ask? I'll show you.
Wacky.
Here's what we're doing, and there's two ways to write it, and they mean the same thing, but you're going to have to recognize both of them. Okay? The first is, if I decide to model this, okay, then the amount, this is sort of like the interest rate. The amount I have equals the starting amount, which I'm going to call the initial amount.
You sick though.
He's just decaying and losing his unstable particles. The amount I have at any moment equals the initial amount. Well, what's happening to the initial amount?
It's decreasing by a half. So
It's decreasing by half, so it's either dividing by 2. I'm going to write it as being multiplied by 1/2.
No, that. I'm gonna go the opposite there.
Now, multiplying times 1/2 makes it half as big each time. Okay? Now, this is the part you don't have to know yet, but we're going to get to. How many years have to, well, I'll say, how many years have to pass before you actually get half of what you started with?
10.
10. Okay? So we don't actually, one way to think of this is it's like you don't actually multiply by the 1/2 until the 10 years go by. In order to make this model do that, here's the trick. If it takes more than, yes?
Is it always going to be 10 years?
No, different things have different half-lives.
Okay.
Here's why we're afraid of nuclear weapons and radioactivity so much. Plutonium and uranium, the two radioactive materials that we use to blow up entire cities,
Yeah.
have half-lives in like the hundreds of thousands of years or tens of thousands of years.
Awesome.
Which means if you make a place radioactive with plutonium or uranium, it's going to be very radioactive for a long time.
Yeah.
It'll get, I mean, it'll take like 10,000 years for there to be half as much radioactivity. Unless we actively clean it up, and there are ways to do that. But that's what makes it so scary. Because that's like, there's a city now where they've cleaned it up enough where they think it's a tourist attraction. Have you guys ever heard of Chernobyl?
Yeah.
You've heard of Chernobyl, actually, yeah. It's a place, it's in Russia. It's not in the Ukraine, or is it in the Ukraine?
I'm not sure.
It's
Okay,
in Russia.
Chernobyl. It's in the former Soviet Union, but I forget whether it's Ukraine, Georgia, Russia exactly. But it's where in 1986 a nuclear reactor had what's called a meltdown, where it got to the heat that was used to produce the energy got too hot, the reactor broke, and it released clouds of gas. And the Soviet Union, bless their hearts, didn't tell anybody. And all of a sudden, all the milk in Poland was radioactivity, because that's where the wind blew the gas. And the Polish people were like, why is our milk radioactive? They actually evacuated an entire city, which is now a tourist attraction. They finally gotten the radioactive levels down enough so that you can go there for brief periods of time. They give you a Geiger counter to register radioactivity,
That's nice.
and they say when this starts clicking really fast, run. They also make little strips that slowly change color. And when they change, it's like a mood strip. When they change color to a certain level of brightness or darkness, you've taken a certain amount of radiation, you have to run. You'll be fine if you get out in time. But you can actually take short tourist trips to this city where everyone just got up and left because there's a cloud of radioactive death heading towards them. Short answer, it's not always 10 years.
No, they're just
Okay.
random
Mimi.
abandoned cities in the former Soviet Union. Just
Yes.
completely, people just picked up and left.
Yeah, there's always a reason behind it, but yeah, Nimi.
And how do you go from 0 to 110 to 50? You go lower.
I said it was a half-life